Hello everyone, my name is Nigel and today I'll be presenting my final year project on the real-time simulation of on-load tap changer transformer using Typhoon Hill. Now, I know that sounds quite technical, but don't worry, by the end, you will see how this project tackles a real-world problem that affects us all. Whoa, what is going on here? Looks like we're seeing some flickering here. Ever had this happen at home? Annoying, right? This flickering light is a simple example of what happens when the voltage in our power supply becomes unstable. But what if we could prevent this? That is where my project comes in. I will show you how we can stop this from happening using a technology called the on-load tap changer, or otherwise known as OLTC. Before we dive into the OLTC, let us go back to something you might remember from high school physics. Remember these transformer diagrams? In simple terms, transformers either step up or step down voltage. But here's where things can go wrong. If the transformer doesn't control the voltage properly, bad things can happen, like this poor guy. Don't worry, we're not dealing with ghosts here, but we're dealing with something equally tricky, keeping the voltage stable and safe. That is where the OLTC comes in. So, what is an OLTC? OLTC is a key device used in transformers to adjust voltage levels without cutting off the power supply. In simpler terms, it acts like a dial that adjusts how much electricity flows, keeping everything balanced. Think of the OLTC like a dimmer switch for your lights. The OLTC switches between different tabs or settings to bring the voltage back to the right level. Now, how do we know whether an OLTC is working? That is where the simulation comes in. Now, you might be wondering, what exactly is Typhoon Hill? It combines two key ideas. Typhoon, representing power and dynamic, and Hill, which stands for hardware in the loop. This lets us test virtual versions of equipment like transformers on the computer instead of real hardware. And together, Typhoon Hill gives us a real-time platform to simulate OLTCs. This real-time capability is what sets Typhoon Hill apart from other software. Unlike many of these other software options, Typhoon Hill lets us see the system operate live. This makes Typhoon Hill the perfect tool for this project. To simulate OLTC operations accurately, we need a reliable model of the power grid, and that is where the IEEE bus system comes in. But what exactly is an IEEE bus system? Do we just combine the term IEEE with a bus to form an IEEE bus system? Well, it is not about buses like the one in the image. An IEEE bus system is a model that shows how electricity flows through a grid. For this project, we are using the IEEE 33 bus system. It is a widely recognized model because it strikes the perfect balance between complexity and usability, making it ideal for sliding OLTC behaviors. Now that we have covered the bus system, let us talk about the load flow analysis. Load flow analysis helps us determine how electricity flows across the network. We input data like bus information into the system. The analysis then outputs key factors like power losses and voltage levels. These outputs help us assess the efficiency and stability of the grid. Now that we have covered the load flow analysis, let us talk about how we perform it. We use numerical methods which helps us predict how OLTC will behave under different conditions. There are three common methods. First, there is the Gauss-Seidel method. Next, the Newton-Raphson method. And finally, the fast decoupled method. And for our project, we choose the Newton-Raphson method because it converges quickly, providing reliable results in less time, which makes it ideal for our complex system like the IEEE 33 bus system. Now, this brings us to our problem statement. OLTCs are costly to produce, and physical testing is risky, making software simulation a safer and cost-effective option. However, traditional simulation tools like MATLAB only provide static analysis. This is where Typhoon Hill comes in. But there's a challenge. There's not enough research on Typhoon Hill's effectiveness for OLTC simulations. So what does this project aim to achieve? The main goal is to develop a real-time simulation of OLTC transformer operation using Typhoon Hill. We have three key objectives. First, we will build a detailed real-time simulation of the OLTC in Typhoon Hill. Next, we will analyze how it performs under different conditions. And finally, we will evaluate how effective Typhoon Hill is in solving real-world challenges. To achieve the project aims, we will need several key resources. The primary hardware is a laptop, which will run all simulations. The core software is a Typhoon Hill, and we will also use MATLAB as a comparison. So, how are we planning to achieve our project aims? We start by developing the simulation models using Typhoon Hill and MATLAB. Next, we will integrate the OLTC model into the bus system model. Then, we will validate the result by testing how the OLTC performs under different scenarios. And finally, we will optimize the settings through repeated simulations. Now, how do we test whether this OLTC model is actually working when integrated into the bus system? First, we have the accuracy test, which focuses on three key comparisons. Active power, which is the power used to do useful work. Reactive power, which helps maintain voltage levels, and the voltage profile, which shows how voltage level varies across the system. Next, there's the behavior test, which focuses on how different factors like load models, tap ratio settings, and PV curves impact the system. And before we dive into the results, let us quickly break down a few important concepts to help us understand how our test works. First, let us talk about the different load models. A constant power load always consumes the same amount of power, a constant current load always keeps the current steady, and a constant impedance load means both current and voltage change proportionally. Remember the transformer we discussed earlier? The OLTC tap ratio is what helps keep the voltage steady. By adjusting the taps, the OLTC can raise or lower the voltage by maintaining a stable range. And lastly, PV curves show how power transfer and voltage stability are connected. Now that we have discussed how to achieve our project aims, let me present the final result. And ta-da! In this newly developed OLTC model in Typhoon Hill, the three-phase voltage source provides power, the transformer adjusts the voltage, and the RLC branches represent the transmission line and load. Now that we have looked at the individual OLTC model in action, let us see how it fits into the bigger picture. And here is the final integrated schematic of our model. This system models a real-world power grid, where green line shows power flow points and brown lines represent backup pathways. Tie switches control these paths for reliability, and the OLTC helps regulate voltage in real time. Now, let us see the IEEE 33 bus system in action. Now, this real-time simulation shows how each bus element and load interacts within the network. You will be able to observe the voltage levels and power flow at each bus node changing as they adjust in real time. Now, we have also developed an interface that tracks key parameters like active power, reactive power, and voltage. It also shows OLTC performance by displaying the PV curves. Now, let us move on to the result of our accuracy test, starting with the active power comparison. The first graph shows the active power comparison between MATLAB and Typhoon Hill before compensation. With a maximum difference of 14.5%, after applying OLTC compensation, this difference drops to around 2.6%, showing an 11.9% improvement. And just like the active power, the reactive power for both simulation models follows the same trend. In the first graph, we compare the reactive power between the two datasets before compensation, with a maximum difference of 14.4%. After applying OLTC compensation, the second graph shows this difference dropping to 2.3%. This is an improvement of about 12.1%. Moving on to the voltage profile, the first graph shows both simulation models following a similar trend across the buses. The second graph confirms this, with the highest percentage difference being less than 1.01%. These three key results confirms that the Typhoon Hill OLTC model effectively stabilizes voltage across the bus system and that we have successfully created a working model. Now, moving on to the behavioral test. This test confirms if the OLTC works correctly under different load models. The graph shows the voltage profile before and after OLTC compensation for the three load models. Before compensation, there is a noticeable voltage drop as we move further from the source. After compensation, the voltage levels of the three load models are much more stable across all models. Now, let us see how OLTC tap ratio settings impact power transfer across different load models. In all three load cases, power transfer increases as the tap ratio rises, peaks, and then slightly drops. The difference is in how steep the drop is and the value of the ideal tap ratio, with the constant current load model showing the steepest decline and the highest ideal tap ratio. Now let us look at the PV curve analysis. The first graph shows that without compensation, as the tap ratio decreases, both power transfer and voltage drop. The second graph, with compensation, shows improved power transfer. The third graph shows that higher load compensation further improves power transfer. Overall, these three results prove that adjusting OLTC settings and load compensation boosts power transfer and reliability. In summary, this project modeled the OLTC transformer using both MATLAB for static analysis and Typhoon Hill for dynamic simulations. We created schematic models of the OLTC and simulated them in both software to compare results. The results obtained show good alignment between the two simulations, with Typhoon Hill capturing real-time conditions more effectively. So in conclusion, the OLTC model developed with Typhoon Hill successfully simulates OLTC transformer operations, enabling other engineers to exploit various operational scenarios without the need for costly physical testing. Key findings shows a 12% improvement in power transfer with compensation. The Typhoon Hill model matched MATLAB with less than 1.01% difference. Constant impedance loads were more sensitive and reducing the tap ratio lowered power transfer. These findings contribute to better OLTC operations, aligning with SDG 7, and these findings have been submitted to the SETA journal and the manuscript is currently under review. Thank you very much for watching.